Before we start, just a reminder that you can submit a discussion topic, an open problem for Friday, and it's not recorded, so feel free to submit something rough, something vague. We will not judge something incorrect, just something interesting. And for the first talk, Ben Brown is going to give us a tutorial on Floquet codes.
Hi, this is on now. Hi, everybody. Thanks for having me here to speak to the organizers. Happy Valentine's Day. I am going to talk about Floquet codes. So this is these are introduced by Hiram Hastings, as I'm going to mention on the next slide, but I'm going to introduce them in a way that we wrote about them in a paper I wrote with Marcus, and then I'm going to say a few other things around it as well. Okay. So this is kind of wild that there is a tutorial about it already, because it's the first paper on Floquet codes only appeared in 2021, but everybody got really excited about it. So to say a little bit about why that was exciting, Ha and Hastings, or Hastings and Ha, they were what they showed was you could realize a toric code-like phase using only 2 body measurements, and that's very exciting from a practical perspective, because experimentalists like doing low weight measurements. That's really nice. And but they seemed pretty mysterious at the time. At least the way they explained it seemed very mysterious at the time. I hope I can demystify that a little bit. But they were the way they put it forward in the first place was they tried to compare Floquet codes to, say, a subsystem code. And if you try and use, say, a naive subsystem code-like description of these models, then it kind of looks as though they have no logical qubits, or at least the examples we looked at. So the first example they proposed, which we tend to call the honeycomb code, seems to have no logical qubits. That doesn't have to be mysterious, and yeah, as I say, I hope I can demystify that. Okay, so the way I like to think about it, well, there are several ways. I'm going to go through a few, but we have a lot of success with coming up with quantum error correcting codes by comparing them to phases of matter, condensed matter physics and topological phases. And so I'm going to give a very physical description of how we can think about Floquet codes in terms of anion condensation. And there are going to be certainly Margarita's talk that's appearing after mine. She really uses these concepts quite a lot to come up with some logical gates in terms of Floquet code logical gates, and that comes from this physical picture that I'm going to give you. Okay, so I'm going to first of all talk about anion models in the vacuum. Then I'm going to introduce the color code, which I used to derive the honeycomb code and a lot of other codes. Then I'll talk a little bit about error correcting with these codes and the microscopic picture. And I want to spend, as it's a tutorial, I want to spend a few slides at the end talking about maybe future directions or other works that other people have done in the few short years since this first paper appeared, and maybe interesting directions to go in the future. Okay, so to begin with, I know this is a computer science institution, so I should say a bit about justify how the physics of these things work. So in, and I guess what you've been talking about all week, sorry, I missed the beginning, but I'm sure stabilizers have been introduced. So normally when we talk about error correction, we talk about a quantum error correcting code, which is some subspace of a larger Hilbert space. And we specify that Hilbert space, or that subspace, using stabilizers. And the common +1 eigenspace of a commuting set of Pauli stabilizers tells us the code space of that code. Now in physics, we like to talk about the energetics of things, and we like to talk about Hamiltonians. So we can easily jump from a quantum error correcting code written in terms of stabilizers to a Hamiltonian by taking all the generating set of stabilizers and writing the negative sum of those. So we're always interested in physics, we're interested in the lowest energy eigenspace, which is the smallest eigenvalue of this matrix I've written down, this Hamiltonian H. And the way I've defined this Hamiltonian makes it such that the ground space, which is the lowest energy eigenspace of this Hamiltonian, is the code space of this code. Okay, but now the Hamiltonian is also good for, why are you waiting? Do you want to come in? You're going to stand in the door? Do what you want, it's fine. Okay, so we also like talking about the energetics of things. So as well as having the ground space, or the code space of these codes, we can also talk about the excited eigenstates of this term. So we can take things, yeah, okay, so if we add errors to a code, some of the stabilizers are violated, and in this condensed matter physical picture, this corresponds to energy or quasi-particles. So for example, here's a picture of the toric code. Here I've drawn a logical operator. But now if I write down a new operator that's maybe a partial support of this logical operator, it's going to violate some of the stabilizers. And you can see exactly where those stabilizers are violated. There's a very specific location for those. And we can regard those as quasi-particles. And in all the 2D models I'm going to be talking about, these quasi-particles are anyons, and these have special properties that tell you about the model that we're studying, or the phase that we're looking at. Okay, so the Floquet codes that I'm going to talk about, they give rise to the toric code phase. I trust everybody's familiar with the toric code. But we have the particles that we have in the toric code. These are anyons. And there are 4 different anyons in the toric code. One of them we call the electric charge. Another we call the magnetic flux. These are called as such because there's an analogy with the Arison-Balmer effect, where if you braid an E charge around an M, you pick up a non-trivial phase. This is what's special about anyons. You don't see these kinds of effects in 3 dimensions. It's special to 2-dimensional topological codes. There is a fermionic charge, which is the combination of 2, an E and an M. So we call this fusion, and I'm going to say a bit more about that later. And the one we tend to forget about, but I'm going to talk quite a lot about, is the vacuum, which says that there is no particle at some given location. Okay, and we can describe these phases by topological phases. We tend to describe by the particles we can create on these systems, and we classify the particles we create by what I already mentioned, fusion rules, but also the braid statistics that occur when we start exchanging these charges with one another. Okay. So yeah, I want to spend some time talking about the vacuum. People tend not to talk about the vacuum because it means there's no particle there. So just give me a little moment to talk about nothing at all. Okay, so let me tell, with regards to nothing, here are some things. I told you, like when we talk about anyons, we've got to talk about what happens when we braid them together, when we bring them together, and when we exchange one with another. So, okay, if I have nothing here and nothing here, and I exchange that nothing, like what happened? Okay, good. Nothing happened at all. So this is what we call an exchange statistic. And if we braid nothing around nothing, no phase is collected. Like that's different from the E and the M I discussed before. Okay, if I take some other particle and I combine it with nothing, all I have left is still that. Okay, so this is a fusion rule that says if I take some other anion and I fuse it with nothing, I still have the same thing left. And finally, if I complete a whole monodromy, which means I have a particle and I braid a vacuum all the way around and put it back to where it began, nothing changed. So that's that, okay? Okay, that's the vacuum. And this is an anion that we do have to think a bit about when we consider anion condensation for Floquet codes. Okay, so now let me say a bit about the color code. So the color code has a bunch of anions associated to it. It's a stabilizer model that we define on a 3-colorable 3-valent lattice, like a hexagonal lattice. You can see all of the faces can take a color such that they don't touch another one of another color. And on every single hexagon, we have 2 types of stabilizers, a Pauli X stabilizer, which is the product of X on all the corners of the hexagon and a Pauli Z stabilizer, which is the same but with Pauli Zs. And again, it has a bunch of excitations associated to it, like E's or M's in the case of the toric code, and they're related in a way, and I'll explain that shortly. But in the color code, we have colors associated to the charges as well. So I can create color code anions, charges, particles. I'm using all these words synonymously with strings. If I say add a string of Pauli X terms that terminate at some green plaquettes, then I make a green charge on both of the opposite green plaquettes. And the color of the the color of the charge is determined by the color of the plaquette that I've violated. Okay. And so all these charges also need a Pauli label associated to them. And I determine the Pauli label by the Pauli operators I use to create that string. So in this picture, sorry, it's quite small, but there are two Pauli X operators that create a string along this edge. They violate two green plaquettes, so they're green, and I use an X string to create them, so they're Pauli X, they're green X charges. You can also look at the microscopics of the color code to see the fusion rules of this model. So I can make other colors of charges like a red and a blue as well as a green. And if I bring, say, a green charge and a red charge together, they can be combined to make a blue, as long as they all share the same Pauli label. And likewise, I can take three charges of the same color with different Pauli labels, and they fuse together to give the other type of Pauli label. So for example, here I have a red X and a red Y, and if I bring them together, they fuse to give a red Z charge. That's the color code. Okay, so it's quite helpful for me to consider the color code in terms of what we call.
Just to clarify, when you say bringing the charges together, you're actually doing like operations on the qubits of the code, right? So that would be like flipping one of the bits between them.
Yeah, that's right. That's right. So it's because we're working with Pauli operators where they're their own inverse. It's sometimes it's not completely obvious what I'm doing, but yeah. So like if I were to apply this XX term, I've created two green particles at the endpoints. Now, this is also a hopping operator. So if I already had a green particle and I wanted to move it from here to there, I can apply another string operator that will move it across the lattice. So, and yeah. So for example, here I had a Y charge, and here I had an X charge, and I moved them together with two Y terms and two X terms. And then what I should have left behind is a red Z term, which I then move with another hopping operator up here. So I'm really moving them around the lattice.
Maybe it's helpful to say, so when you say particle, you mean like violations of certain types of checks, right? And
yeah, that's right.
It just means splitting bits, and it kind of changes the violation. So.
Yeah, exactly. So as I was saying before, in this Hamiltonian picture, there are some energy associated to violated stabilizers. So when I say excitations, I really just mean some like specific stabilizer check at some specific location, which is well defined on a 2D lattice. So that's what I mean by particle. Sorry, I thought I saw another hand. Okay. Right, so it's pretty handy for me to talk about the color code charges on what I call the boson table. This has been useful in a bunch of papers. So as I said, all the color code excitations that I'm going to be talking about, they have a color and a Pauli label, and it's good to arrange them in a grid like this, where colors are arranged through the columns. So all the red charges are in this column, all the green charges are in this column, and all the blue in this column. And likewise, the Pauli labels, they share rows. So all the Pauli X excitations live in this row, all the Y excitations live in this row, and all the Z excitations live in this row. Okay, and there's a reason for this. So first of all, let me talk about these color code excitations. So first of all, if I take two of the same color code excitation and I exchange them, I don't pick up any phase. That's boring. In physics, that means this is a bosonic charge or a boson. That's what bosons do in particle physics. Okay, so if I pick any one of these charges, so this, this table is classifying all the bosons of the color code. I did mention fermions before, and I can make fermions by combining certain bosons together, but I don't need to talk about that too much. Okay. So as I said, this table is also useful for describing the fusion rules of the color code, because if I take two bosons from the same row, I get the other boson from that row by fusion. So for example, in this picture I showed the green X and red X are fused to give the blue X. Well, the red X and the green X gives the blue X. And likewise, a red Y and a red X can give a red Z. So a red X and a red Y can give a red Z. So those are the color code fusion rules. And the other rule, and this is maybe most important for the rest of the discussion, is what happens if you exchange or braid a color code anion around another one and put them back in their locations? What phase is collected? And well, this table is set up in such a way that if you choose two bosons from the same row or the same column and you braid them, you get a trivial phase, you get +1. But if you pick two bosons from different rows and different columns, so for example, a red X and a blue Z, and I braid one of those all the way around the other and put them back again, I get a -1 phase. So that's going to be quite important. Okay. So now, let me tell you about condensation. I've set up the color code. Now I can tell you about condensation. So what condensation means is I pick an anion from my anion model, and I want to put that in my vacuum. So this is why the vacuum was important at the beginning. So I'm going to change what it means to be the vacuum now, and this is going to change the physics of the phase. So for example, I'm going to pick the red X charge, and I'm going to say this is going to be a part of my vacuum now. So I'm going to use this symbol to mean identification with another charge. So I've written here that the red X is identified with the vacuum. And yeah, so on my boson table, I black it out with a big black smudge. That means condensed. Okay, but now what consequence? Like I've told you the rules for an anion model. So now let me tell you the consequences of this on the other anions of the model. So remember, for a well-defined anion model, the vacuum has to respect these rules. The vacuum has to braid trivially with itself. It has to exchange trivially with everything, and it has to fuse to give itself. So if the red X is now a vacuum charge, then this has consequences on the other anions of the model. Do you have a question? You can think about it that way. I prefer not to use too much maths terms, but my co-authors do like that. Okay. Right, so the fact that I chose a boson from the boson table, and as I told you, exchanging a boson with itself gives nothing, that's okay. The fact that I chose to condense a boson means the vacuum is consistent with itself. Okay, but now some anions braid trivially and some anions braid non-trivially with this red X anion. So I told you before that if you're in a different row and a different column, if there are two anions that are in different rows and different columns, then their braid statistics are non-trivial. So since red X is now in the vacuum and I'm only allowed anions that braid trivially with the red X, all of the anions that are in different rows and different columns, they're now illegal. They're what we call confined. So I've crossed those ones out in this table like that. However, there is still a non-trivial anion model left because all the anions that are in the same row or the same column as the red X, they still braid trivially with the red X anion. So those are still allowed. So if these are confined anions that I've crossed out, the anions that live in the same row and the same column as red X, those are deconfined. Those are still perfectly legal. So I get to keep those. However, there's one more thing to check, and that's fusion. So if you remember fusion with the vacuum, this is supposed to give the same charge back. So this still has consequences on the remaining charges. So here's the thing. Back in the color code model, so vacuum has to fuse to give itself back. Vacuum fuses with A to give itself back. But from the parent model that was without any condensation, the red X fuses with, say, the blue X to give a green X. So that's not quite allowed yet, because what we really want, if red X is a part of the vacuum, that I were to fuse blue X with red X, I should get blue X back. So I can make that the case, but what happens in this condensation operation by putting red X in the vacuum, it means really that green X is identified with blue X. So I now regard these as the same thing. And by the same argument, I have to regard the red Y as being the same as the red Z. Those are now identified as well.
Could you comment on how to, like, microscopically, if I'm thinking about codes and...
I'm going to do that soon. Yeah, that's like 3 slides ahead. Maybe, I can't remember how many slides ahead, but that's my guess. Okay, so look, now we have, here's our anion model. Here's our anion model that we have. I started with the color code. I condensed the red X charge, and that made all of these crossed out anions confined, and it unified these deconfined charges. Green X and blue X are now the same charge, and red Y and red Z are the same charge. So I've given them little smudges with the same colors each. So these are bosons in the same thing, and these are bosons in the same thing. But because they share different rows and columns from each other, they also braid non-trivially with one another. So the model I've just made is a model with 2 bosons that braid non-trivially with each other, which is exactly the toric code model. So I can unify, say, these guys with an E charge and these guys with an M charge. And by condensing a red X charge, I get the toric code model.
Sorry, what do you mean confined?
They're illegal. You don't get them anymore. Okay. Right. So yeah. Sorry. This is what you wanted. So right. So physically, what do I have to do? So I want an anion. I want a code where if I try and create some red X excitations, I just get a trivial change to the model. So I can go from the color. I can do this condensation operation microscopically by projecting my color code model onto a model that has the hopping operators for the string operators that move these red X excitations around. I need to add those operators to the stabilizer group. So if I take the color code model and I measure all of the red X edge terms, which are the hopping operators that move the red X charges, then that's the same as having condensed the red X charge in the color code model. So that's what I have here. That's what this picture is showing. I started with the color code with X, Y, and Z plaquettes and all the colored faces. But now I've measured all of these red XX terms on these red edges. So those are now a part of my stabilizer group. And that means if I try and apply a red XX charge to hop a red X, the new model doesn't change. So these red XX terms, they also commute with the blue face terms and the green face terms because they share 2 sites. So I keep all of the X stabilizers and the Z stabilizers on the blue and the green faces of this model. But I have also lost some stabilizers. When you measure terms that don't commute with your stabilizer group, other stabilizers get kicked out. So where I used to have an X stabilizer and a Z stabilizer on the red faces, the Z stabilizer doesn't commute with these new red terms, these edge terms. So I threw out the Z stabilizer. So that's why I've drawn a red X on the X faces, because there's just one X stabilizer there now. Okay, and you can really see, if you go back to the toric code picture, that the model I made here is really a toric code model. So if you're familiar with Kitaev's toric code paper, where you put qubits on the edges of some lattice, and star operators are associated to vertices, and Z stabilizers are associated to plaquettes, then that's exactly the model we have over here. where there is a star term on every vertex, and these two-body vertices as well. And there's a Z stabilizer associated to all the plaquettes, which are these six-body triangles. And here on this picture, I've overlaid the color code, the condensed color code model with the toric code picture, and you can see they just line up exactly. So in this sense, you can think of this condensed color code model as being a toric code model. So that should have answered. Are you not paying attention? Okay. Right. Okay. So look. Wake up. Okay. I am. What am I talking about? Okay. So look. So now you know about condensation. You can construct Floquet codes this way. So as I said, you can make a toric code from condensing one of the bosons of the color code. But you can think of the Hastings-Haar model and generalizations thereof as some condensed color code model that gives you a toric code. But then you can continue to perform sequences of condensation operations, which, as I argued, is just the measurement of two-body edge terms, which are hopping terms for these anions. But what's important is you always condense a charge that I've previously confined. So one of the illegal anions. And that's what they are. Yeah, so exactly. So if I have, so you can think of one step of a Floquet code, which is a transformation from one code to another code with two-body measurements, as beginning from, say, this red X condensed color code. And then I map it onto this green Y condensed color code. But so this works out fine as a code because the red X condensed color code and the green Y condensed color code, they both share a pair of deconfined charges. So because this red Y is confined in both models, that remains a deconfined charge throughout the model, and that means I can continue to use the hopping operators of those anions as logical operators throughout this transformation. The same is true with the green X charge. That's a deconfined charge through both of these models, which means I have two what's more, these two charges braid non-trivially with one another, and this means I have a pair of non-commuting logical operators, logical Pauli operators throughout this transformation. Okay, so I think my next slide. Yeah, that's right. Okay, so let me talk through the microscopics of that again. Okay. So it's the same, but this time I condensed the green Z instead of the green X, but I'm sure you've all seen that there's a symmetry between these. Okay, so say I were to start with, how does error correction work? Now I'm back to the microscopic, so this is getting closer to the error correcting side of things from the physical. So yeah, I start with this red X condensed color code, where again, I have X and Z stabilizers on the blue and green faces. I have X stabilizers on the X faces, on the red faces, and I have two-body XX terms on all these bold red edges. And then what I want to do is I want to measure, I'm going to go from this code to this code by measuring green Z edges. So I'm going to start with this code, and then I'm just going to measure ZZ on all these green edges. Several things happen, and I'm going to go through the list. So first of all, so what's going to happen? So some stabilizers are killed. So first of all, these green ZZ edges don't commute with the X stabilizers on the green faces. So when I measure these green ZZ terms, I kick myself out of the eigenstate of the X stabilizers on these green terms, on the green faces, and I'm just left with a Z stabilizer on these faces. So that's the bad news. You lose some stabilizers when you do this. But that's okay, because we get a bunch of other stuff. So another thing we do is we can use the green ZZ edges to infer the value of the red face terms. You can see, because there are green edges living on the full support of this red Floquet, I actually relearn the value of my red Z face. So I've kind of initialized some new face operators by doing this. I don't know why I say kind of. That's exactly what I did. I also measure some stabilizers. So I was originally in an eigenstate of this blue Z face term. So I should know its value. I know its eigenvalue. And if I measure these green faces, I can infer its value again. So this actually allows me to recheck my blue Z faces. So this actually gives me some stabilizer information to recheck the value of a stabilizer. So that's important. So three things happen. Some stabilizers are killed, some stabilizers are reinitialized, and some stabilizers are remeasured, which gives me stabilizer checks. So lastly, you can see that, again, due to the color symmetry of this lattice and symmetry between Pauli X, Y, and Z, you can see that this model is essentially the same as this model, just with a translation and a different basis. So you can see I could just keep making these condensation operations over and over and over again, learning different stabilizers and killing others, remaking others, checking others, so on and so on and so on. And you can pick any kind of sequence you like. And as long as you keep condensing a charge that was confined in the last round, then everything goes fine. So that's how, yeah, now you're paying attention. All right. Okay, so this is the honeycomb code of Hastings and Ha, where they make a sequence where they condense red X and then green Y and then blue Z. So the funny thing, actually, something they like to point out in this paper is that it takes 2 rounds before you bring the code back around to itself. If you go red X, green Y, blue Z, red X, green Y, blue Z, and so on and so on and so on. So one thing, I don't know if I was completely clear about it, but through the transformation, the E and the M have to be preserved. So for example, if I go from red X and I say that these orange spots are my E charges and these blue spots are my M charges, the E's and the M's have to be the same on both sides of the transformation. So if I go from red X to green Y, then this is still my E charge, because this has to be the same as this. And this has to be my M charge, because this has to be the same as this. And so on and so on. So if I go through 2 transformations, I go red X to green Y, and I'm here, and then to blue Z. Well, this one is my M, and this one is my E. So when I go from blue Z to red X again, if you keep following these consistency rules, then you can see that the M's and the E's are swap places. So you have to go 2 times around before you've actually got your original code. Yeah, so in our paper and several other papers that appeared at the same time, around the same time, including Margarita's paper and a Psyquantum paper that came out a little bit later, you can also use these rules to make CSS versions of Floquet codes. So that's what we did just by choosing different sequences of condensations through this path. I guess I'm going to talk a little bit more about that. Okay. But now what I want to do, I'm going to say a bit more at the end about this too. You said I should stop for quick. I'm going to switch to this 3D picture and talk about that for error correction's sake in a moment before I go on to some more speculative things. Are there any questions up until this point?
So what about the properties of the code? So some condensation must be bad. They must give you a poor distance, or
well,
things are preserved.
How do you know that things are what like distance or
Distance, degeneracy?
Degeneracy, as in the
Number of logical qubits.
number of logical qubits.
Like for instance, I could do condensation of one type of onion on one face, another one on another face. I could do some arbitrary things. Some patterns must be bad, right? They may degrade your distance.
How do I know that? So I would say that's something you have to check, and I guess I haven't done it at this stage, right? I'm going to say a little bit more about the circuit picture at the end, but maybe that's a bit more speculative. No, so if I had,
You know, the fact that you speak about onions suggests that there is some topological order.
Yeah.
So there is a macroscopic distance. So it suggests that you preserve the distance.
Yeah.
But
So,
you haven't
so
agreed that.
I would add, okay. I mean, so the way I like to think about this is really just a code deformation, and that's maybe quite well defined in terms of that there's a very clear definition of this kind of thing, right? So I can write down a subsystem code that consists of the stabilizer group of my initial code and my final code, and then you can ask, yeah. So now my terms don't commute entirely because there are stabilizers here that don't commute with all these measurements and vice versa. Now you can check the distance of this code, by looking at this, well, treating it as a subsystem code, and you can ask what's the distance of this subsystem code. And in this case, it's fine, and I can.
I know it works in that case.
Yeah, I know it works in this case. In the general case, I mean, this is how I would check it in general.
Okay.
But I agree, it's not completely clear. But yeah, I mean, here's a case where it's fine. So I would say, actually, let me just add, because I pulled this slide out from the last time I gave this talk, but I am actually free to condense or deconfine charge. And this is the same as doing logical readout. Yeah, I'm not going to prove it to you, I'm just telling you.
But then, just in terms of degeneracy, right? Like, you go from the degeneracy of the color code on the torus to like the circuit code on the torus.
Mm-hmm.
So like that's like one, like, right, you sort of, if I think of I'm starting from the color code, putting that black dot reduces my degeneracy.
Yeah.
Yeah.
Well, okay, so let me just, can I also say, so with regards to the subsystem picture, the fact that these two deconfined dots are the same as these two deconfined dots, that's kind of like saying that they're in the, hang on, so I forgot I had a board. Okay, so if I have the stabilizer group of my red color code and the union of the stabilizer group of my green confined color code, and I say this is my gauge group. So my stabilizers are the stabilizers are the stuff that commutes with my gauge group, like intersected with my gauge group. So that's the same as me saying, when I did this code deformation, that's the same as saying I measured the, I should put this in the slide, that I can use the green Z terms to infer the values of my blue faces. And then my logical operators, which commute with my gauge group but are not members of my gauge group, those elements are really corresponding to these dots, which are in common with these dots. These dots and these dots, they're kind of like dress logical operators, which I get from multiplying it with the edge term. So in this sense, yeah, things are kind of well defined. I don't know how well this generalizes to like general code definition. Let me talk some more about that at the end. I want to say a bunch of stuff about that. Blah blah blah. Okay, so I'm gonna. How do you use these things for error correction? I've talked a lot about physics, but this is an error correction conference. Okay, so what we use, it's really helpful to look in the space-time picture for these kinds of codes. So here I have the CSS color code where I measure green X, blue Z, red X, green Z, blue X, and so on. So how does this give you a stabilizer check? Well, so as I said, at some stage, I measure some green XX term. And this initializes an X stabilizer on a red face. So that means I'm in a known eigenstate of this, and I can use this stabilizer of this plaquette term, and I can use this plaquette term to detect errors, provided I don't kill that plaquette beforehand. So how does that work out? So what happens, what's important is through all of these steps, my two-body terms always commute with the plaquette I just initialized. So for example, I can measure blue ZZ, and that will commute with the X plaquette because blue ZZ edges always touch two sides of this red plaquette. Then I can measure red XX edges because X plaquette will commute with red X edges because Pali X commutes with Pali X. Then I can measure green ZZ because green edges commute with the full plaquette of an X plaquette around the red edge. And then finally, I double check the value of this guy because blue XX terms around the boundary of a red X plaquette, double check the value. So what happens is if I initialize these green XX edges to initialize a red X plaquette, I double check it again later on without having disturbed the value of this plaquette. So this is what STIM users might call a detector cell, where this stabilizer is initialized and detects errors up until the point where you double check it later on.
So when you say double check it, that's like your first actual stabilizer measurement, right? Because it's a comparison between the two.
Yeah, so initially, yeah, exactly. Initially, this is a random outcome. Like I didn't necessarily have an eigenstate of this plaquette when I measured these in the first place. So that gives me a random plus or minus 1. But when I come to double check it, this should be the same as this because none of the edge measurements I've made in between can disturb that. Okay. Right, so in general, this is how I've shown you that there's one surviving X check that goes throughout the code. In general, this is how the detector cells of the different colors are all appearing throughout this code. Here I initialize an X plaquette, and I measured it again over here. So there it was, double checked. But there are also blue detectors and green detectors all occurring around the same time, but not completely in parallel. So let me also add, as soon as I finish making a red X detector, I measure the red Z edges and I kill the value of this stabilizer, and then I re-prepare it again. So this is what I mean when I said you don't necessarily start in in fact, I know you don't start in an eigenstate of your plaquette necessarily. But it's kind of neat because as soon as I'm done measuring this red X detector, I initialize a green X detector as well. That means, yeah, so a qubit. So okay, so also remember that every single qubit sees a red, a blue, and a green plaquette. So what this means is every single qubit always has 2 detectors on touching it at any given moment. So if there's an error on a given qubit at some time, it will violate two detectors. So for example, if there was an error on this qubit right then, there is no red detector there at that point, but it will violate the green and the blue. So that's okay. That's how we can detect those errors, and you can use a min-weight matching decoder or whatever decoder you want that matches pairs of defects to correct or identify and correct for that error. Likewise, you can correct for measurement errors in this model. If a measurement error, say, happened on this edge, it would violate this cell and this cell. So again, a measurement error will just create a small edge with 2 defects at its endpoints. So all of the types of errors, all the basic kinds of measurement errors and physical errors, they're just dealt with as, yeah, they all create small strings and small violations of 2 detectors at their endpoints. Nobody worries too much about hook errors with these things because all your measurements are 2-body, so hook errors end up looking pretty trivial. If you don't know what a hook error is, that doesn't matter too much. Okay, so you can simulate these things. We simulated error correction with a circuit model of the CSS version of the Floquet code that I described. And we got a threshold, so the distance is preserved. Numerically, you can see. There's also, yeah, other people have done these things, Gidney and Mike Newman and Matt McEwen. They did some simulations at Google, and this is a Microsoft paper you're involved in. And they did some simulations of these things as well. So there's some background on numerical results. I hope I didn't forget any other ones. There could be some others by now that I haven't managed to mention. Okay. So I've got 15 minutes left, and I was going to say a little bit about how you can use anion condensation to make boundaries for these codes. I'm supposed to finish at 10 o'clock, right? Okay. I'm gonna.
So so normally the problem with the color code is that every qubit talks to 3 checks, and then the decoder is a pain. So in the past, we've said we'll just map color codes to surface codes by forgetting a check when we try to decode. And so I can think of the Floquet code. Basically, we go stronger than that. We say that at any point in time, there's only 2 detectors per qubit. And then why do I And the only thing that forces me to move is because I have limited myself to wait 2 checks.
What do you mean by move?
The surface code I'm correcting changes in time.
Mhm.
It's because I've limited myself to wait 2 checks.
Yeah, that's right. Okay, that wasn't a question. That is not. That's a comment.
No, okay, so my question is,
Oh, now I got 2 questions. Shall we let Ken, and yeah, we'll come back to that.
yeah, so imagine I have 2 fancier codes in which the difference between them is the number of checks that are talking to the qubit. Can I build similar sort of objects? I want to move away from this planar codes. And so from the coding, from like the, so I imagine I have my parity check matrix. I look for every place where there's 3 things in the column, and I remove one of them, so that all of my things now have two detectors per qubit. Qubit row, column. Seems like I could do that with other, like it's like a way to build it with other codes without having any business, right? I just do.
You could. I would hope you can generalize. I think yeah. These are properties you want in some generalization of a Floquet code. You're kind of you're stepping on my lines at the end.
So normally one big benefit of measuring wave 2 operators is that you can make a relatively short measurement cycle. So here it is extended to, I think, 8, is it?
Yeah, it's quite slow in the end. I mean, yeah, so each of these edges is like prepare, see not, measure, and forget about single digit ones. And you go through a round of 6 steps. So yeah, it's quite slow.
So does it affect the threshold at all?
I mean, compared to, I mean, okay, like the
Color code, for example.
well, you should really maybe compare it to the toric code. The model we have here is a toric code, not a color code. Like here's a threshold. Here's the one I did for circuit level noise.
It's about a third then.
It's I mean, 0.3% compared to, I don't know, I think the surface code would give you 0.6 or 0.7% of the same noise model.
The thing that this one is for a model where you implement each joint measurement using Alextra and Scylla qubit.
Yeah, that's right.
So if you have native joint measurements,
It could be a lot better.
it's much faster, and then the threshold is about 2x the threshold of CNOT based qubits. But it's not. It's hard to compare. It's different types of qubits.
Yeah, it's what it is. Yeah,
It's just a good code for qubits with native joint measurement.
So yeah, I want to. So these slides that I'm now skipping. So hang on, I didn't mean to cut you off. We got to the end of your question. You're good. Okay. So I was going to say a little bit about how anion condensation can be used to make boundaries, and making boundaries for Floquet codes is slightly non-trivial, but it turns out using this parent color code model, we were able to find some color code, some boundary terms for a color code or Floquet codes this way. But this may be a bit more of what I don't need. But what I really wanted to end on, I made a few slides saying other things or other directions, or how are we supposed to think about these Floquet codes? Like a thing that they felt very complicated at the beginning, and maybe I think that there are these big crazy new things with making running error correction with 2-body measurements, but there were no logicals, and in Margarita's paper, you don't even have stabilizers if you want to treat it like a subsystem code. So what are these things anyway? And I sort of prefer to think about if there's something new, I try and make it look like things that I know that are already old. So let me try and say a few things. Okay, so I explained this whole thing in terms of this condensation picture, and that wasn't, I mean, okay, that's because I want to talk about my paper, but that's been useful for other people generalizing Floquet codes as well. So there have been, for example, people have made 3-dimensional generalizations of Floquet codes, and those are in these references here, and they've really kind of come out with this condensation picture by looking at exchange statistics of quasi-particles in higher dimensional systems. So I wonder if this condensation picture can be helpful for generalizing to other types of Floquet codes as well. And let me get more to that. But what I really wanted to say is like, yeah, I would like all of these codes really to be something more familiar that we've been studying for a long time rather than some crazy new thing, which is going to lead to something else. Because I don't think there is any obvious reason for Floquet codes to be something big and special necessarily. I think we should put them back into our old pictures. And I want to just sort of say a bunch of ways that I've tried to think about that. So as I've kind of alluded throughout this talk and here as I was drawing on the board, really these things like a Floquet code or one step in a Floquet code is just a code deformation. Like it maybe this idea of looking at all of the measurements over a full sequence makes things look very messy in this subsystem code picture. But if you look at a whole period of a Floquet system, just step by step, they look a lot more like a very ordinary code deformation. And you know, there's quite a lot of literature now. Christophe Bio put out this paper, and these ideas were also appearing in a paper I was writing around that time of general formalism for code deformations between stabilizer codes. So I feel this should be maybe quite an easy way to try and engineer new Floquet codes. So maybe that's to your question, Ken, or comment, or whatever that was. Another way I sort of like to think about it is like maybe these Floquet codes are just a smart way of measuring the stabilizer circuits for the toric code. I mean, we have a toric code and we just do a bunch of two-body measurements and we get this out. So maybe it should fit into this picture of, you know, we have lots of ways of measuring stabilizers. I mean, with the surface code, we tend to imagine having one measurement qubit and coupling it to its neighbors and then reading out that measurement qubit. And that tells us the stabilizer, but we have also like Schur stabilizer measurements and we have flag stabilizer measurements and all kinds of things. So maybe we should just stop thinking about codes in general and maybe start thinking about circuits in a space-time picture. These ideas have been explored. I quite like these ideas of Gidney and others about relaxing hardware constraints, and maybe there is a nice formalism for describing these in terms of, say, space-time codes, which is, well, Nico has written about this recently, but maybe it stems from Lamia and Dave Bacon's older work. Yeah, it feels like we should just be thinking about codes in terms of the circuits that we use to measure stabilizers, and maybe Floquet codes are just a special way of reading out stabilizers. And there's nothing more to it than that. It's just a toric code with a fancy stabilizer measurement circuit. Maybe, if you were trying to make things easier. So another way you could think about this, and I think it relates to the space-time picture, is a lot of people have kind of come up with this 3D model. Floquet codes have fallen out of this 3D model. Again, this showed up in one of my papers where we foliated the Floquet code. So foliation means you take some stabilizer model or some stabilizer readout circuit and you map it into a measurement-based model. And you end up with this 3D graph that looks a lot like this other model that I would call the Rausendorf model, which is some measurement-based model that's a lot like the toric code model in 3D space-time. But because it's a measurement-based model, the time is mapped into space and it's a 3D lattice. And well, yeah, if you try and foliate these Floquet codes, things look very familiar. And we came up with this graph in the middle here. I'm not the only one to have noticed that. Lots of other people have also tried to write down Floquet codes in terms of tensor networks and 3D graphs. And so a paper I mentioned in the middle by PsiQuantum, they actually came up with Floquet codes independently just by doing transformations on some tensor network graph so they just mapped the Rausendorf model onto the model that I've been describing in 3D, just using tensor network relations to, I don't understand it very well, but they're not even the only ones to have done that either. These other references I've given also came up with or described Floquet codes in terms of a tensor network. Yeah, okay, so that's all I want to say about other ways we should be thinking about Floquet codes. Let me also say some interesting things we should be trying to do with Floquet codes. So the talk we're going to see next by Margarita is on how we can do logic gates with Floquet transformations. So we're going to look at it. I'm assuming it's she's looking at her phone. Let's try to work out what was in your talk. She's got to look at. I think her talk is about color code Floquet codes and how you do gates with those. And so again, maybe the story there is code definitions. And I've also added a citation to some work on how you move twists around this Floquet code I've already described by Tyler Ellison and others. So yeah, like if we're just doing a bunch of code definitions to read out these stabilizers, then maybe we should just be doing code definitions to break twists or holes or punctures or whatever you want. That seems straightforward enough to me. And lastly, another talk we're going to hear about these things on later. You know, if we're supposed to think of Floquet codes as maybe just some nice way or some practical way of reading out stabilizers, then maybe we should have LDPC Floquet codes. And how do we get that in general? Though I don't know. But yeah, an example of some Floquet hyperbolic codes is going to be discussed this afternoon, I think. So yeah, okay. Maybe it would be nice if we could find some generalization, like Floquet codes, or let's say Floquet is some way of reading out fancy stabilizers in some nice practical way. Then maybe we should be able to do that with all kinds of LDPC codes. But at least we have one example showing that this is in principle possible. I guess we'll hear about that later. So yeah, it's I don't know. I ended here by trying to make it sound quite boring what Floquet code is, because I feel that's a good way to generalize these things. But you know, they're still very exciting. It's nice to see that there are practical ways of realizing codes with practical architectures, and so hopefully I've given some people some ideas for ways to go forward in the future. I think I'm done. Thanks.
So you said how, I mean, you talked in terms of these like anion condensations, right? And if I understood you correctly, this is equivalent to saying that we're moving from like one gauge fixing of some parent subsystem code to another, moving one set of stabilizers and throwing away stuff that ends it conveniently, right? But if I want to look at this process in terms of like anion condensations, to what extent does the underlying model have to have this like trivalent, tricolorable property?
Oh, that's not necessary. That's really just this is a tutorial. I was just using an example that definitely works and the easiest to know.
What other geometries could we like, extend this to?
That's a good question. I guess, so it seems like you need models with a lot of symmetry. Again, I think maybe we'll hear more about it a bit later on. It feels like, to me, I feel like the recipe is having a parent model that's got a lot of extra anions that can be condensed and have a lot of space to. This maybe gives you a lot of options for finding measurement sequences that give rise to fault-tolerant codes. I don't know. That's a good question. Yeah.
Any other question, comment?
Thank you for the tutorial. Could you clarify, so like you mentioned about like running the decoder, so like with the detection cells, once you do those like 6 rounds or something where you are able to check those parities, so you run the matching only every 6 rounds of the two-body measurement, is that right?
You run, well, I mean, it's just, again, it's like really like the error correction with any 2D code. You collect a large space-time history and you decode a big sort of D by D by D size block all at once. Yeah, it's like I said, it really comes out in, say, if you look at this in the measurement-based picture, with some appropriate lattice geometry and applying the construction due to Rasensdorf from 2006, these codes just come out. And then it's pretty clear that you have primal cells and dual cells, and you just run matching. Yeah.
And in this picture, like, is there any connection at all between somehow like the number of rounds you have and the distance of the code?
I mean, it's got to be of order D. I can't think off the top of my head. But you can work it out. I mean, you can count all the least weight fault paths. And if you want to, I mean, these things generalize to do, say, lattice surgery operations or whatever surface code operations, you can puncture braiding. And again, it's just always important that boundaries are spatially separated in the space-time picture. So yeah, you just have to go through carefully and check. Yeah, I can't quite do it off the top of my head, but yeah, you have to measure it kind of all the details.
So I have one quick question for you. So you like this picture of onions?
Mhm.
When I see that, I'm convinced that it's pretty, which is a good argument for using it already.
Mhm.
But if you have to convince someone who comes more from coding theory with a classical intuition,
Mhm.
why do you think we should adopt this picture? What does it try us? What is the main thing that we get out of it?
What do you get out of it?
This got
I mean, I'm not trying to persuade anybody to adopt it necessarily. It's been helpful for me to. Well, what I like about it is, I mean, just having this whole story. I really want all the way back to the beginning here. I like it, I think it's nice having this window between this condensed matter picture and this coding picture. It means there are lots of things we can import from the condensed matter picture into error correction and vice versa. Like certainly when I was a PhD student, all of error correction research, as far as I could tell, was on, say, self-correcting quantum memories, which was right in the middle here, right? And you can discover things like Haas qubit code, which is both an interesting error correcting code and also a phase of matter, and it's kind of it steered both of them. Yeah, I like having this language to translate from one to the other. And I don't know, the anion picture also gives you nice ways to hand wave away quite a lot of the technical details of error correction. So I find that to be very helpful.
Yeah, okay. I can comment again. So I used to hate the color code because I thought these red, green, blue charges were kind of useless. You're actually kind of giving up information about the code to try to make it a nice physics picture. Mm-hmm. What I liked about your discussion of these different Floquet codes was how the condensation had really helped with the boundaries.
Mm-hmm.
So it's like an example of how somehow the physics picture helped solve this coding problem, which is like, what do I do with my edge?
Yeah, no, I like that too. I'm sad I didn't have quite enough time to talk about it.
Yeah.
Okay, yeah. Thank you. So we have